consider f of x equals sine x when x is greater than or equal to 0, and it's x squared plus 5x when x is less than 0. So we need to prove that f is continuous but not differentiable at x equals 0, and then we need to write down f dashed x as a piecewise defined function. So something like this. It might be a good idea to have a look at the graph. So remember, you've always got a calculator there if you like, and if you don't know how to start a question like this, having a look at the graph is probably quite a good option. So we go into menu and graph, get rid of anything that you don't need anymore, and I'm going to write down sine x. So y equals sine x, and then we have the domain that it's over, so that is between 0 and, well, it's just 0 and it up to infinity, so 0 and then just put a little comma in and leave that blank. And f of x equals x squared plus 5x, x squared plus 5x, and that is when x is between, well, from 0 and downwards, so 0 is going to be our upper bound on this one. So we're going to have just that comma and then a 0. Okay, so hopefully that works. Right, so we're definitely going to need to change the window radically. X min, so we definitely need some negatives, so let's go down to, say, I don't know, minus 5 maybe. Can always change it up to 5. Y min, probably maybe minus 5 and 5 again, but this sine x is only going up to 1, so I'm tempted to go more like, I'll go up to, say, minus 2 and 2. And then hopefully we'll see a bit more of the graph the way we want it. Okay, so that's not bad, although I am missing a bit here, so maybe I want that on. So let's just increase our y min a little bit. Try and get that maximum, that minimum in, so maybe minus 10, minus 5. Okay, that's not bad actually. So if we just sketch that, and the key bit we're interested in is when x is 0, that's the boundary bit. So we have this sort of nice parabola here, goes up to 0, and then you can see when we start turning into sine x, so all the way here it's x squared plus 5x, and then you can see it's clearly not as steep when it goes to sine x, so then it sort of does something like that, and then it'll just sort of keep doing things like that. Okay, so that's f of x. Right, so I probably could have exaggerated that a bit. I really wanted to show that it's a steeper line here and not here, because that's a very important part of the question given what we've been asked to do, to show that the thing's not differentiable, right? So we need to prove that it is continuous but not differentiable when x equals 0. So remember, if we start with being continuous, to be continuous, firstly f of a needs to be defined, a in this case being 0, so we need to show that f of 0 is defined. So f of 0, well, it says when x is greater than or equal to 0, f of x equals sine x, so that would be sine 0, and sine 0 is 0. And then we need to show that the limit as x approaches 0 in both directions, the limit of f of x, we need to show that they're both equal and that they're equal to 0. If all three of those conditions are true, then the function is continuous at x equals 0, and you can clearly see it's continuous everywhere else anyway. We know a bit about sine x and we know about basic quadratics. So the only real issue is this bit here. Right, so the lim as x approaches 0 from the left-hand side of f of x, well, that equals the lim as x approaches 0 from the left-hand side of x squared plus 5x. And for a nice continuous function like x squared plus 5x, you really can just think, well, if x was 0, what would this be? It's clearly 0. If you don't like that, you could always, just to confirm, you could always do a little trace. And I'm not very good at switching lines, so I think you do it with the up and down arrow. And you can see we're approaching 0. We go to 0, 0. You can see it's getting very close. So that's just 0. In the other direction, the lim as x approaches 0, the positive of f of x, well, that's going to be the limit as x approaches 0 from the right hand side of sine x, which hopefully we know. I mean, you can just see it's 0. Right, so that's good news. So f of a is defined. The limit as x approaches 0 of f of x, as x approaches 0 of f of x equals 0, which equals f of 0. So f of x is continuous at x equals 0. So it is continuous there. Right, now we need to show that it's not differentiable. So basically, we need to think, well, does this limit, well, to be differentiable, you have to be continuous. So it already is. It's met one criterion, at least. But then we need to consider the limit as x approaches 0 of f dashed x in both directions. And then look, if you look at part B, it does ask us to write f dashed x as a piecewise defined function. But actually, I'm just thinking about it, it's probably quite useful to have that piecewise defined function before we do this bit. So I'm going to write that down now. F dashed x equals, well, we get our piecewise notation. Approaches from this side, we know the derivative of sine x is cos x. We do need to be careful about the interval we're giving this over. So actually we can only consider an open interval. We can't include 0 in this because 0 is clearly an issue, because as we will formally write down later on, you can't say that the derivative's necessarily approaching the same thing from both sides. I mean, just looking at the graph, you can clearly see that it isn't. So I'm going to say it's cos x when x is greater than 0. I've dropped the or equals to, right? And it also equals, well, if you think of the other side, this was x squared plus 5x. A simple polynomial derivative will tell you the derivative is 2x plus 5. 2x plus 5. Again, open interval. It was open anyway for this one. So when x is less than 0. So that piecewise thing should allow us to identify these limits from both directions very easily. You certainly don't need to do any first principle stuff. So now the limit as x approaches 0 from the left-hand side of f dashed x, well, that equals the lim as x approaches 0 of 2x plus 5. Which 2x plus 5, just think about it, it's just a nice linear function, continuous everywhere. So it's literally 2 times 0 plus 5. Plus 5, which equals 5. Okay, other side, lim as x approaches 0 from the right hand side of f dashed x equals the limit as x approaches 0 from the right hand side of cos x. Okay, well, you should know cos x. I mean, I would draw it, I don't really have room, but cos x, cos 0 is 1, and either side of that, it's still 1, so it's clearly 1. So now we have a problem because the derivative is approaching 5 if we approach from the left hand side, it's approaching 1 if we approach from the right hand side. So therefore, lim as x approaches 0 from the left hand side of f dashed x does not equal the limit as x approaches 0 from the right hand side of f dashed x, which tells us that the limit as x approaches 0 of f dash x does not exist. That tells us that f of x is continuous but not differentiable at x equals 0. Okay, for part B, we've already kind of answered it. As I alluded to earlier, we kind of used the piecewise definition for the other bit, but now we can really talk about it properly, because you need to make sure it's indifferently to the original piecewise function. You can't include 0. Basically, the derivative is undefined at x equals 0 because it's not converging to anything. There's clearly a disconnect in the derivative. You're approaching 5 from one direction and 1 from the other. So actually, the derivative as a piecewise function is completely undefined when x equals 0. So the piecewise function for the derivative f dash x equals, have your nice curly bracket, and it equals cos x when x is greater than 0, and it equals 2x plus 5 when x is less than 0.